Welcome back, MEFB 2013213 manufacturing processes. Hi all, I hope you're doing very well today. Okay, so today we're gonna talk about electrochemical machining. Yeah, so this is another micro machining process. Like I always mention to you, yeah, this topic is specially dedicated for machining or micro machining, where you're actually removing material in its micrometer and nanometer level. Okay, if you could remove material normally, you do not want to use this process because this removes very minute processes. The normal lathe milling, metal cutting that you do in the lab remove material in big chunks, yeah, but here you're removing material in minute level, micrometer scale, nanometer scale. That's when you choose to use this process. So normally all this modern machining or non-traditional processing is used when you need precision, okay, when you want perfect dimensions to the dot, to the spot, yeah. So that's when you use micro machining or all this electrical discharge machining, electrochemical machining, ultrasonic machining. So let's look at electrochemical machining today. Yeah, what is electrochemical machining? I'm sure you would have done electroplating way back in your form 4, form 5, if you recall correctly. Yeah, so if you remember what is electroplating, in electroplating you have your anode and cathode, correct? And it's immersed in an electrolyte. So your anode is going to be the material that you want to coat. Okay, so plating procedure, yeah. So say your anode is made out of gold, your cathode is your chain, okay, your chain. So what happens is it will, once you when you switch on the circuit, it will remove material which is the gold from the anode, flow through the electrolyte, and it will deposit onto the cathode. Cathode is your chain. So you're actually doing plating of your chain, gold plating of your chain using this technique. So electroplating is normally to coat or plate objects to make it look more attractive. Okay, so you have your gold plated chain, gold plated earrings, gold plated rings, okay, through this method. So having the same concept in mind, electrochemical machining is just the reversed of electroplating. Your aim here is to machine, to remove material, not to coat material. So we're doing just the reverse process here. So the principle, an electrolyte acts as a current carrier. So you're going to immerse your anode and your cathode in the electrolyte, and normal electrolyte will be salt solution, yeah, NaCl, natrium and chloride. So the metal ions from the workpiece or the surface anode are discharged. So when the metal ions are discharged, you are removing material, but you're removing material in its micrometer, nanometer level, yeah. So the metal ions from the workpiece, surface or anode are discharged using potential energy between the tool and the work. So if you look at it, your workpiece is anode, your tool is cathode, okay, and the potential difference between your workpiece and tool is the one that determines the ability to remove material. So you will remove ions from the workpiece, flow through the electrolyte and deposit onto the, by right it should deposit onto the tool, but in this case you're not doing a plating procedure and you do not want to damage the tool. So what happens is you will remove material from the anode, which is your workpiece, flow through the electrolyte, and before it could plate on the tool, we will accelerate the electrolyte movement and direct it into a filter, so your tool is safe. So if you look at it, the tool, presence of the tool there, the tool does not do any machining, yeah. The tool is just there as a cathode to complete your circuit. Okay, so if your cathode is not there, your circuit is not complete, the electrochemical machine would not function. So your tool is present there as a dummy in the place of the cathode, and your workpiece is there in the place of the anode. So before the, like I mentioned to you, before the ions or before the material have a chance to plate on the tool, they are washed away because of the high rate of the electrolyte movement. So if you look at the diagram, electrochemical machining, yeah. So you have your electrode over here. This is your electrode, negative, and this is your workpiece that you are machining. Yeah, positive. Workpiece must be immersed in a tank, and there should be supplied, or there should be electrolyte, yeah, electrolyte flow within the workpiece itself, and electrolyte, the excess electrolyte would be directed into the a separate container, or we call it a sludge tank. Yeah, so like I mentioned to you, you have the anode, workpiece, cathode, tool, and the potential difference between anode and cathode is sufficiently high, then you have metal ions removed from the workpiece. It will flow, and by right it should deposit onto the electrode, but we accelerate the electrolyte movement, and we would direct it into a sludge tank. So all the material that is being removed together with the electrolyte will go into this sludge tank. Okay, and then here the electrolyte will be filtered. Okay, and the new fresh electrolyte will be directed into the system again, and then the second round of material removal will take place. Material is removed, the material removed plus the electrolyte will be directed into the sludge tank. From the sludge tank, it will be pumped into the electrolyte with the material, or the removed material will be pumped into the filter. Filter will clean it up, and then the fresh new electrolyte will flow in. So this process will go on and on and on until you've achieved the dimension that you want. As I mentioned to you, material removal rate is in micrometer or nanometer, and you have a mainframe to monitor the material removal rate in the X, Y, and Z axis, and you can actually direct to accelerate the electrolyte movement in the X, Y, or Z axis. Yeah, so that is electrochemical machining or micro machining. So basically in electrochemical machining, your tool is made either from brass, copper, or bronze. But as I told you, yeah, the tool is dummy there. It's just to complete the circuit. It's not machining. It's there just to complete the circuit. The electrolyte is highly conductive salt solution. Here we're using sodium chloride, yeah, or natrium chloride, the same thing, yeah. Advantages, hard or soft conductive metals can be cut. Again, keyword here, conductive. So it is meant for conductive metals only. Non-conductive metals cannot be machined using this process. No heating is produced. So there is no heat. So there is no frictional, you won't have frictional force or damage due to frictional heat. Yeah. No metallurgical changes, as high temperature does not occur. So since there is no high temperature, you do not have any changes in the material properties. And tool can be made from soft and easily shaped metals, as there is no contact between the tool or work. So as I told you, that the tool is not doing the machining. It's not machining the product. It's just there to complete the circuit. So you do not need to have a tough, hard density, hardness, fracture toughness tool. No. It can be any soft tool as well, because the tool, as I mentioned to you over and over again, the tool there is present just to complete the circuit. It gives you good surface finish and no sharp edges on the work. So you do not need to have deburring. Yeah. Okay, our next process, laser beam machining, electron beam machining. Yeah. So laser, what does laser stand for? So laser is another, if you go to industries, people actually use laser to cut materials, right? I'm sure you've seen the laser pointer that you use sometimes. Yeah, when you're doing presentations, you may use a laser pointer, but that's very, very basic, baby level of laser application. The real level of laser application is seen in the medical field, where they actually use laser to remove cataract from the eye. They use laser in industries to actually cut metals. Yeah. So laser, what does laser stand for? Laser, light amplification by stimulated emission of radiation. So laser is reality, a very strong and intense beam of light that is highly collimated. This beam can be focused optically onto an area. So you focus the light, okay, they focus the light on a particular spot, and you burn, or you actually create a cutting edge cut there, and you start cutting the material just by burning the material at that particular spot, and you cut. Yeah. Types of lasers, you have ruby or glass laser, CO2 laser, liquid laser, semiconductor laser. So if you look at the structure, yeah, this is laser beam. So like I told you, when the laser emits the light, it can penetrate, it will burn the material to that region, and it will cut the material. So if you look at this, this is your structure of your laser. Yeah, you're using a ruby crystal, you have a power supply, you have reflecting mirror, so the laser or the light is amplified through, and then you have a partially reflecting mirror, it goes through the lens, and it is focused on the workpiece. So when it focuses on that particular workpiece or particular spot, it's going to burn the material at that particular spot and start your machining process. So you cut, it'll burn the material, and cut the material all throughout until you complete the entire process. Okay, you have something else called electron beam machining. Electron beam machining is the same exact concept as laser beam machining, except that if you look at it is also used to machine materials, right? It's also used to machine materials, but instead of using light amplification, laser use light amplification, electron uses electron beam amplification, meaning that you're replacing the light with electron beam. Okay, so same conduct, you have a high voltage cable. Okay, you have a cathode, anode, you have the valve, and you are going to shoot the electron beam to the workpiece, and when you shoot it at the workpiece, it's going to create machine that workpiece at that particular point, and then you go on and on and on. The only difference between electron beam and laser beam is that electron beam is done in a vacuum chamber. Okay, so you see the entire structure is protected in a vacuum chamber. What is vacuum again? Vacuum is a space where there is no presence of air. There's no presence of air. So because it has got high radiation, yeah, so like it's just like conducting an X-ray. So you need to make sure that the region is protected in a vacuum chamber. Okay, so unlike laser can be done in an open environment. There's no danger of radiation, but electron beam is not like that. It has to be done in a protective environment. So electron beam machining is a lot more tedious, because you need to create a vacuum environment in order to conduct the machining process. Okay, I would like to stop here. I will see you all later in class. Thank you.